Good afternoon or good evening, depending on where you are in the world, and welcome to today's Battery Tech webinar, The Use of Artificial Intelligence in Quality Control, sponsored by Lupine Research, a division of Weiss-Aug Group, and broadcast by Informa. I'm Michael Krieger. I'll be your moderator today. We have just a few announcements before we begin. First of all, the webinar is designed to be interactive. The dock of widgets at the bottom of your screen will allow you to learn about today's speaker, download resources, share this webinar, and participate in the Q&A session that takes place at the end of our presentation. The slides will advance automatically throughout the event, and toward the end of our webinar, we'll ask you to complete our survey found on the right-hand side of your screen. Please take a minute to fill this out before leaving us today, as your feedback provides us with valuable information on how we can improve future events. Lastly, if you're experiencing any technical problems, please click the Help widget found at the bottom of your screen or type your issue into the Q&A area, and we'll be glad to offer one-on-one assistance. Now, on to the presentation, the use of artificial intelligence and quality control. Discussing today's topic is John Francis, Vice President Automation at Lupine Research, a division of Weiss-Aug Group. To learn more about John, please visit the Bios widget. John, over to you.
Thank you. Welcome to everyone who's interested in learning about the use of artificial intelligence and quality control. As was just mentioned, my name is John, and I'm with Lupine Research, and we're a division of the Weiss-Aug Group. The Weiss-Aug Group is a larger company. They have about 7 manufacturing facilities in the U.S. and Mexico. The Lupine Research, we have a state-of-the-art facility in Boulder, Colorado. We perform technology and development for Weiss-Aug. We develop manufacturing techniques and automation equipment. We have a very close relationship with our customers and Weiss-Aug, and we solve difficult or challenging manufacturing problems. Our automation division, which I am part of, my expertise is in machine vision and deploying artificial intelligence to solve machine vision problems in primarily quality control. I also work on measurements, integration, robot positioning, or data acquisition and logging. So if you have questions about any of this or what we do, please feel free to type them in the widget, and we'll be sure to answer them. The agenda for today's discussion is going to be an overview of machine learning using deep learning, the types of algorithms that I would typically deploy for machine learning. Case studies, I have 2 examples that I'm going to talk about. First being a high volume application for automotive, and the second being a more precision application for medical. Lupine Research, we have metrology equipment that we sell and develop for our customers. And so I'll go through a couple of those ideas for you towards the end of the presentation. The first slide that I have, I want to talk about why we're interested in deploying machine vision, particularly AI-based machine vision in quality control. And the reason that comes to mind first is replacing visual inspections. Manual inspections can be tedious, prone to fatigue. Results can vary across operators. As you know, this is, a lot of times when you're having an operator take a look at something and judge its subjective quality, the results can vary. They can exist, in each individual person can make a slightly different decision. And that's the number one reason why we might deploy our AI-based algorithm to make a decision, is because the way that these are assembled is by generating thousands or even millions of images and developing an algorithm that can make the best decision across the data set. And it's a little bit different than what you would do with a human operator. Obviously, you'd have to train them. And the machine vision idea here using AI becomes very scalable and easy to update and move across plants. So it can make very consistent decisions. They can be moved around. And we have, gigantic databases just based on the way that we have to assemble the algorithms. And I guess last point I might say here is it's not traditional machine vision. We're making qualitative analysis here. And I have my next slide kind of highlights that a little bit. Where in traditional machine vision, we might be doing something like pixel counting or counting the rice grains or looking at the edge of a can or doing some sort of discrete measurement of a diameter or a fiducial. So I would like to say that traditional machine vision is more measure, locate, count type of ideas. With machine learning, we get into a more qualitative analysis. We can develop a continuum of states where go from the smallest defect type that you can imagine all the way up to the most gross or glaring. And the example I have here is pretty obvious, but you can imagine that developing an algorithm to differentiate between what is seen as the braid in this tube on this slide versus the actual defect could be pretty difficult. But when we have a bunch of examples of the good and the bad, we can build an algorithm that can analyze each pixel in that part. And so from machine vision using AI, I'd like to say that there are the types of algorithms we're going to deploy are more pixel analysis or classifying the entire image as a good or bad or something, or locating some type of feature in the image. And all of these, we would use data sets of images to do that. And I'll go through each one of these individually here, starting now. Analyzing a defect would be taking each pixel in the image and judging its probability for defect, which is the real difference from traditional machine vision. We're looking across the whole image. We're deciding on the probability of the defective area being in this location or not, and then we're grouping those pixels together to score them. And I have a couple of examples here that I think really highlight the strengths of this type of analysis. Where we're looking for a chip on a white background, or we're looking for damage on some sort of material that has a lot of texture on it, or perhaps something more obvious like a scrape, where there are normal scrapes due to the geometry of the material, and then there are scrapes that we're trying to identify as exceeding some sort of threshold, or in conditions where the lighting is difficult or defects are really difficult to highlight, we can apply these algorithms to train out the nuances, as in the dent I have in this image down at the bottom right. The second type of algorithm we would typically deploy in machine learning would be a classification algorithm. This is more what you might see in traditional machine learning, machine vision applications, but here specifically applied to quality control. In this example, I have 3 different images, each showing the probability of classification. These are basically just a black surface on a metallic shiny surface, and you can see we're training the algorithms to identify whether it's a bubble or a good part, or a part that is escaped its boundaries here, as in the overflow on the far right. Any number of groups could be classified using a classifier. A lot of times we'll use this to tell us something about the defect type. So if you're looking for a scratch and then you're trying to classify how that scratch was either generated through the process or some other way. The last type of algorithm that I would typically deploy in a machine learning application would be locating parts, particularly locating parts that are, you couldn't solve with traditional machine vision. And so parts that can't be solved with location problems that can't be solved with traditional machine vision would be an example here, where we're locating a tip that might not even be obvious to the viewers, but we're trying to find the tip of a part beneath a silicone jacket. And the ML algorithms turn out to be really great at this, because it's picking up on all sorts of nuances in the image. And then another example would be here, where we're trying to look through another opaque or translucent body in order to identify something behind the material. And in this case, we're looking for either a spring location here in the upper the part of the image, or maybe it's an O-ring location here in the bottom. And we can even train these location classification algorithms to say something about the quality of that O-ring placement, or say something about the quality of the spring placed here, or I guess another example in this image that's a little bit harder to note is that we might be using the location type algorithms to locate fiducials on the surface that aren't as obvious as a through hole. For example, the parting line between these 2 pieces of plastic here. Um, Locations can be bounded by any number of parts. We could say, oh, you're looking for three, or we could also say something about the nodes. You could say, if you were trying to find the hands and feet and body of a person, you could train a node model to find those together, and it could become even more robust. When we deploy machine learning based algorithms, the process goes something like this, where you take a bunch of sample images, usually thousands or tens of thousands. They get labeled, whether it's labeling the entire image or labeling specific features. We train a model, and then we test a set of images, whether it's 10 or whether it's 10% or whether it's 1%. At some point, we are having to test some number of the sample set images. And that test, we can graph, and whether it's a graph that looks like a matrix of probabilities, known as a confusion matrix, or whether it's a graph of two different probabilities, whether the good was classified as good or the bad was classified as bad. But essentially, we're validating the specific results of the model by doing some sort of statistical analysis on sets of images that are not included in our training set. And this can be very helpful, and in many ways represents a real paradigm shift in the way that we're doing qualitative analysis on parts. So, and by that I mean, rather than having an operator fill out a matrix of good or bad, we're having the machine learning algorithm look through tens of thousands of images and then tweaking the model so that we get the best results in the most repeatable process. And then once you have that model established, you can deploy it into your application. And then once it's deployed, the model doesn't change. And I know that this is a question that comes up to me often, is we're deploying a model into a situation where it's making a decision. Is that model going to change in real time? And the answer is generally no. It could in some cases, but it's really difficult to validate in the type of applications that we're usually seeing. And so once the algorithm is deployed, then we can take a look at the process, make sure it's running properly. And if we see variation in the process over time, then we can go back and add that variation into the model and make sure that it's making a decision based on updates in the process. And it can be a lot easier than retraining an entire staff of people to reanalyze the parts in a new way, whether you're getting a new manifestation back from your customer or whether it's just a change in the process itself. The first case study I'd like to talk about are these disks, which, generally speaking, they're just a round, flat disk. But the round, flat disk can have a few manifestations that I don't describe here in these images, but you can imagine these cover a large variety of part numbers. Some of them have holes, some of them have notches, and we're using the algorithms to detect things like cracks and chips and other type of manufacturing processing defects that come along with these. And the real challenge here, and the reason why I'm highlighting it, isn't because this is a very bland disk. It's more because the process deployed here was for an automotive application where we're looking at 5 parts per second. The parts are moving at 11 inches per second, and each of these parts we're taking about 9 images each. So the math works out to be around 45 images per second that we're processing using very detailed ML algorithms. So what the point I'm trying to get across here is that we can deploy the ML algorithms in situations where the parts are moving quickly, in situations where we have a lot of volume, and get them through our processor. And there's a lot of people, when they think about ML applications, they think a lot of processing time, and that is true, but we can overcome most of that. Another reason why I like to talk about this slide is because as in traditional machine vision, a lot of the problem starts with getting the lighting right. And we have 3 examples here: bright field imaging, where the light is coming, roughly the same axis as the camera, coming down on the part and reflecting back in. A dark field lighting where we're trying to see surface defects coming in from a high angle, and then some specialized lensing that helps us get the edge of the part from the top view. And then when we deploy our algorithms, we can train them in order to look at each one of these individually and qualify each of these images individually and group them in ways, and then make the decision-making architecture such that we can take the decision from each of the classes, the bright field, the dark field, and the edge, and come to the overarching automation with a single decision point. And so at the end, when it hits the pass or fail bin, it's using it's using all of these images combined, so that we're making sure we're seeing the part entirely. The next slide on this topic is the example of what we're looking for. And you can see here, there's actually, why I like this image and why I chose it specifically isn't because it has a tiny crack on it, and we can see the power of the algorithm in order to differentiate. That is true, but it also has some debris in the field, which we're not trying to classify. And so we're able to train the algorithms to differentiate between things that it identifies as potentially debris and things that it identifies as potential cracks. And we can put these in the larger sorting equipment where you're aggregating the decisions from several cameras, or 5 cameras in this case, and coming up to that single decision point. The second case study that I'm going to talk about quickly is a medical or a high precision application where we're looking at the jacket or the exterior of a catheter system, starting at the beginning, going all the way to the end. And we're looking for both quantitative measurements like diameter, outside diameter, or position of certain features. And then we're also training in things that are surface variation, whether it's peeling or damage caused from the manufacturing process. We're developing equipment that can acquire this image data at a really high bit rate, about 48 megapixels per second. It can concatenate all of those images into something that we can pass into our ML models. And then we can take a look at the surface map of the catheter. We can take a look at the contrast map. We can develop a user interface that has partner control so that it can tie back into the quality control system of the factory. And as I mentioned, we can use both the algorithms, the AI-based algorithms, to do both the quantitative and qualitative processing of these catheter systems. This equipment basically took the form of 3 laser profilometers where we pulled the data, both a height stream and a contrast stream from the laser profilometer. We lay the images together so that the algorithms can look at 360 degrees of the catheter at any given location. And then in the end, the machine that we deploy here replaces a 15-minute final inspection with a 60-second scan. And I think the real value here is the ability of equipment like this to combine all aspects of the final inspection, whether it's, like I said, diameter measurement or the surface analysis. A quick review of the machine learning that we're deploying for defect inspection. I believe that the use of AI here in quality analysis is groundbreaking and addressing a very expensive aspect of manufacturing, and that is, where we have people making subjective or qualitative decisions about a part. Our rule of thumb in this is, if an operator can classify an object within about 2 seconds, whether it's looking through a microscope or looking at it, with the naked eye, we can usually duplicate that process with a machine learning-based algorithm with lower cost and higher consistency. We have a lot of experience developing machines that perform these tasks, and we have a lot of experience putting together validation plans that can put this type of algorithm to work quickly and efficiently. The next phase of this PowerPoint, I'm going to talk a little bit about the types of equipment that Lupine Research develops to do this. whether it's a standalone visual inspection machine, a Cartesian robot. We have some special expertise in round wire inspections. And the machines that you see here on this slide, where we have some sort of custom integration with the one at the top left, which we call an ellipsometer, or the one in the bottom right, where we're developing a camera system to look at 360 degrees of a part simultaneously. Our standalone visual inspection machines, typically we're deploying a camera system, lens system that fit the application, and we're going to develop an algorithm or a lensing system that gets the right pixel size so that we can build algorithms that see the right features in your part. We can deploy large or small machine learning computers. The example I have here is similar to what we deployed for the very high volume, 45 frames per second processing computer. We can build custom integration software, software that communicates between the machine learning software and the overarching automation in a way that makes it really easy for operators to just select a part number, start a new routine, and hit go, and then the machine will just pass and fail parts as trained. But I guess the other thing we'd like to say in this slide is that Lupine Research can also help you train, whether it's engineering or operators, to update these models in a way that they can be deployed into our automation equipment quickly. The next machine that we also offer is a Cartesian machine with optical grade Cartesian robotics, high megapixels cameras. I have 9 here, but that it's easy to get cameras off the shelf up to even with C-mount lenses, probably up to 20 or 40 megapixels. We match the application and the optics. A machine like this becomes extremely versatile, and that's why I'm talking about it. You can imagine trays of parts going into a machine like this, and then the machine comes in. It will take an image of each part, find the fiducials. It might be doing some sort of measurement routine. In this case, you can see we have maybe not as obvious, but we have an integrated interferometer to do height measurements. And then we have cameras to take pictures of the things that were measured in order to judge the subjective quality of each of those using the AI-based algorithms. Again, part number controlled machines and integrating with existing quality control software. The last type of machine that we specialize in would be a round tube inspection. Here is one example of that type of machine where we deploy 4 cameras to take pictures simultaneously so we can see all the way around the part. We might be integrating an optical micrometer, which I have shown here as an example. It would go back here so that as the parts move through, we can do the subjective and the quantitative analysis simultaneously. A machine like this could fit a wide range of round parts, and I have some examples of the types of things that we're looking for on those parts on the next slide. You can see, looking for debris, looking for bent wires, looking for blisters, as we've already shown, or even a really great application of AI would be looking through the tube wall to the interior diameter in order to look for very subtle variation in the part color that you can see here in order to identify those internal peeling. The machines that we've developed, designed to save production time and to improve product quality, Lupine Research, we offer consulting and training. We can help others deploy these algorithms using Cognex, or we can deploy LabVIEW-based integration. We can also do partial integration, visual inspection, software components, whatever it might be, in order to solve a automation challenge. And lastly, as the examples show, we do turnkey solutions, complete systems that kind of solve the entire measurement and qualitative analysis issue simultaneously. Thank you. That concludes my presentation, and now I'm going to move on to answer questions. So hopefully we'll get started.
Terrific. Thank you so much for that, John. But before we begin the Q&A, I want to ask everyone to direct their attention to our webinar survey available on the right of the presentation window. And if you close the survey, you can reopen the widget by clicking the icon along the bottom of your screen. Thanks in advance for filling out the feedback form. Your participation in the survey allows us to better serve you. I also want to mention, John, that people can see you at the Battery Show this coming September 12th through 14th in Novi, Michigan, where you guys, I understand, will be at booth 2027 there. So just a reminder, if you're going to be at the Battery Show, you can look up John for some one-on-one time with him. So let's get right to our questions. Hold on, we've got a bunch of them coming in. To participate in the Q&A, just type your question in the text box located to the right of the window, or click on the Q&A icon at the bottom of your screen. If we can't answer all submitted questions, we'll be sure to share them with John, who can reply to you offline. So let me start out. Our first question comes from Akash, who wants to know, are you using semantic segmentation or instance segmentation?
We're using instance segmentation for the most part. It's a little bit of a gray area, but hopefully that answers your question.
Marcia would like to know, are there other ways to find anomalies other than using a threshold or clustering?
I think I'm going to try to answer this question with maybe by adding to it in some ways. The way that we look for anomalies in these images is by training the pixel locations, right? So they're getting cut out in some way, and then going into the training algorithm, and then coming back with basically a trained model that is a weighted matrix. And that trained model is really not doing segmentation in that specific sense. When we segment it, what we're doing is we're getting the pixel values that are high, and then we're deciding, okay, imagine pixel values can come in between 0 and 1. So anything above 0.5, we're going to say, we're going to highlight those pixels, and then we're going to measure their size or group them together. And that is where you see the highlights in the slides. Basically, we're saying, okay, these pixels were grouped together, and then maybe in some cases we were even saying pixel groups that were smaller than a certain threshold, were throwing them away.
Okay, great. Thanks for that. I hope that answered your question.
Me too.
Michael asks, for higher volume applications, are there difficulties with maintaining low inference/processing to satisfy cycle times? And how do you combat those limitations?
Hang on 1 second. Can you repeat that? Honestly,
I can repeat it, and it is a two-part question. So for higher volume applications, are there difficulties with maintaining low inference or processing to satisfy cycle time? And how do you combat those limitations? We could ask Michael to clarify that question if you like.
I think what for high volume applications, how do we get the processing time down in a way? For example, the disks we showed, the images are gigantic, right? They're 9 megapixel images. How do we pull that processing time down? And the answer is, the first answer is big computers with parallel processing, right? So we try not to put, we try not to say, well, here's what I'm going to say. We don't process everything in series. We process them in parallel. And we use several parallel GPUs in order to each one gets its own imaging stream, basically. And that is the greatest way to reduce processing time. The other thing in that application specifically is we develop an algorithm that processes and say, because computers it can be really difficult to force the processing time into a specific window. And so we have to target something much, much lower in order to get the statistical distribution of the processing time to be adequate for our application. And in that specific application, we were looking at 200 millisecond cycle time, but each individual images we were trying to process in around 50 milliseconds. And so we changed the sensitivity or the sampling size within the image in order to match that. Obviously, there are some real trade-offs there.
Okay.
I think.
Michael, I hope that answered the question. If you have a follow-up, just let us know. Clement says, thanks for the presentation, John. Do you use CNN networks of multi-layer perceptrons in general?
In general, all of these are CNN networks, and they are many layers deep. We can, depending on the, I talked almost entirely of images, but we can, absolutely build specific models. We don't ever really get out of the CNN model, though, I think is what you're asking. And we don't. We almost always use the CNN, but they can be one layer if we're dealing with other data types, is what I'm trying to say. They're usually multi-layer if we're dealing with something like an image where we're trying to extract, specific features, right? You're trying to do some sort of, some things help the processing, like locating edges first and then processing the image.
Okay, great. Thanks for that. Charles wants to know whether ML-based machine vision can be used for quantitative measurement.
Yes. What we do for that would be, obviously kind of going back to the examples where we're identifying the pixels that we think are of interest, usually a defect in this presentation. And those pixels of interest, we're grouping them together, and then we're measuring the specific pixel size. It can be really helpful to do things to your optical system in order to make that job easier. For example, using telecentric optics to make sure that your specific pixel size matches something in real world coordinates. And then once you can do that, you can measure the size of that defect or its specific location using traditional machine vision techniques, what area or position.
Okay. Kevin asks, are there any other applications for machine learning in battery manufacturing besides vision systems?
Oh, I would answer that the answer is probably yes. We're talking almost entirely about vision here again in this PowerPoint. But there are some, if you're thinking about quality control, so if you have a particularly noisy data stream, a lot of times, you're looking for a blip on a continuous curve or something like that. Some sort of data structure you can imagine that might not be image related, but is similar in the sense that you have a value of integer, an array of integers of some kind, and you could train algorithms to process an array of integers of any kind, looking for any kind of detail that you can imagine, whether it's a sound bite. For example, if you were trying to listen to a motor or something, and you knew that a motor would be defective if you heard a rattly sound, you could train an algorithm to find that rattly sound pretty easily. Hopefully that answers your question. I don't have any specific examples for batteries, I would say, but you can imagine the generalities here would encompass that. Okay, that's my answer. Okay.
It's muted while I was asking you that question.
Okay.
And it is thus. Michael has a follow-up. What does your group do with images acquired and the results from inspection? Is there data for metrics and results on individual objects within a single image?
Yes, I think the two answers here. Generally, up to reasonable limits, we would be keeping what we can. For example, if we had a process where, the high volume process is a good example here. We don't save the goods we don't save the bads, but we might save the in between, like where it's somewhere along the line of the continuum where we specifically want to add more detail into the model. And so we might say, okay, we'll save everything between, specific results, A and B, and then we'll go back and we'll add those into the model and retrain and revalidate if we can, if it's easy. Other things in terms of metrics, you can imagine we might be looking for a defect of some kind, but you might also be counting the number of parts in a tray, and so both of those metrics would then be kept. I guess maybe let me restate that. The size of the defect, the number of parts in a tray, or the location of a potential might be kept in some sort of CSV file or a database specifically that you could go back and look at for quality control.
Okay, a question from Akash. Are you using transformers?
I don't know. I'm not using transformers.
Okay, great. Follow-up from Clement, who says, thanks for your answer to the first one. And John, you said that data sets are labeled, but do you sometimes unsupervised training? We can't always know all imaginable defects before seeing one.
Of course. I haven't had a lot of luck with unsupervised training in manufacturing. Maybe it's the size of the data sets we're working with. Maybe there are other specific reasons. In general, I agree that there's no way to know all specific defects, and there are always things that are going to fall on either side of the line. But your specific use case might be a little different than mine. I just haven't had much luck with unsupervised training because we haven't really been able to qualify an unsupervised process.
Mm-hmm.
What we do we have the operators label, you go through a phase, maybe the initialization phase of the process where you're bringing it up to speed, where you have an operator in tandem, like a safe launch basically, where they're using the equipment in a similar way. Maybe they're using it as a microscope and they're labeling those images. And so we try to capture as much of the process beforehand, as much of the process variation is what I was implying beforehand, and then build that into the model. And we highlight areas where we think the model is deficient, and we try to improve that by finding examples that look like that. So what I'm trying to say is we have the operator supervising the model and specifically bringing forward cases where the model is incorrect in order to add that into our model.
Okay. Another question from Akash, who asks, which instance segmentation model usually perform best in terms of trade-off between speed and accuracy?
Let's see here. I would have to go through, and I don't think I have the data to answer that question right now. So
okay.
Basically, let's maybe you can email me and we can catch that offline.
Great.
Because I just don't really have the exact data for you at this time, but we can talk about it.
Terrific. Another one from Michael, who asks, I would think that you could build proprietary models using an aggregate of images from many applications of the same type. Do you maintain ownership of the images from your customers?
Yes, you could build a proprietary model. I haven't had, yes, we can absolutely use the images from our customers in most cases, not all cases, but most cases. Once the machine gets deployed and into production, then things get a little bit different. But at some point, we have gigantic data sets of images that have defects of all types. We haven't been able to build a overarching universal model. What we have done is we've been able to build a first level, this one is good at identifying features within an image that then turn out to be defects. And so the first few layers of the model get reused all the time.
Ricardo wants to know whether this system could be used to detect defects or missing or wrong components on printed circuit boards.
Yes, absolutely. An application where we've done that a lot, in particular where you you maybe not need you may not need AI in certain situations where things are really obvious. Like if you have a missing capacitor, for example, it's not there because the color's wrong or something. But you may need AI in cases where you have capacitors from three different manufacturers,
Right.
and you're trying to group those in some way, or you're trying to say this one got the red dot and that one didn't, or some sort of weird, more qualitative reason why on the circuit board you have this component that has that you're trying to capture variation that would be very, very difficult with AI, without AI.
Peter says, to the best of my knowledge, a big issue is the discrimination between good and bad. The big challenge in production is the setting of the threshold between good and bad. How do you handle that with your procedure?
Absolutely. It's always the trick.
Yeah.
Is once be careful what you can see. We're setting up a camera system that is usually a little bit better or has better vision than an operator would be able to have in many cases. And the reason why we're doing that is to make sure that we can set up that clear line between yes, it exists or no, it does not exist. And
Hmm.
sometimes this can be a real point of contention. And I think the answer that you're looking for, the question, uh, is how do you validate that the machine is doing an adequate job as with the human operator. And it really comes down to testing. And so you're going to need to be able to test, get a set of parts or a group of parts that you can run through process A being the original process and process B being the new machine learning based process, and make sure that there's a statistically relevant improvement there. That's how
Okay,
we.
terrific. Another question from Michael, who wants to know, how do you deal with massive labor or time involved with labeling large data sets? Does every image need to be labeled and verified?
Uh, Not every, and actually, okay. So there are a couple ways that we approach this problem. If you can deploy a system to get the existing operators to help label, i.e., we build a camera system that might be a microscope. Can you get a team of people that are qualified to inspect these parts to label these images in a way that makes down the road it easier for us to train? Because once the images get labeled, whether it's by an operator or by an engineer, then they can exist in a data set and be retrained many, many times. Um, the other way that we approach that is once you've started to establish the bounds of your classification, sometimes going back through the data set and having it not self-label as in unbounded training, but having you go back through with highlighted differences between the images can make it quite a bit more efficient.
Okay. Robert would like to know if you could elaborate on the difference between traditional machine vision and AI-based machine vision.
Sure. Traditional machine vision is what I would typically call like you're able to do some sort of mathematical morphological processing that can find whatever you're interested in, whether it's a filter or some other type of process. You can apply that to a single image and then get the same results with every single image that comes thereafter, because what you're doing is basically just math, whether it's a threshold or whether it's a morphological operation. With machine vision, we're taking a set of images and training specific pixels and then creating a weighted matrix to try and then go back and make that same decision. So the real difference becomes that what comes out from machine vision is maybe numerical in many cases, not most cases binary. What comes out from the machine learning model would be like a statistical percentage, whether it's
Mhm.
99% positive or 1% positive.
And let's wrap up. We have one final question from Reza, who wants to know, can you please describe a validation procedure that you've had experience with?
Sure, I'll go back through that. I guess I've hinted at it a couple of times. We've had validation procedures where we generally have a set of parts, let's say the golden parts or whatever you want to call them. And the set of parts, the size, the quantity should cover most of the variation that you're trying to identify. Particularly have good examples on either side of the line of the decision. And then we'll run those through some number of operators, whether it's 5 or 500, depending on the process. And then we'll have the model or the machine. I guess in many cases it becomes a machine because it's a combination of both the image that we're taking and the decision that is being made on the image. So the machine's going to take the picture, it's going to judge it, and then we're going to go back and we're going to look at those two data sets and make sure that the machine is doing a better job.
Terrific. And that's all we have time for questions today. I want to thank you. We appreciate your time and expertise on today's topic. Also, thanks to our sponsor, Lupine Research, a division of Weiss-Aug Group, as well as to everyone in the audience. We appreciate your attention and participation. Within the next 24 hours, you'll receive a personalized follow-up email with details and a link to today's presentation on demand. Please feel free to invite your colleagues and peers who may have not been available to listen to the event. I can also remind you that you can see John and more of this live at the Battery Show in September 12th through 14th in Novi, Michigan. They'll be at booth 2027. This webinar is copyright 2023 by Informa. Presentation materials are owned by and copyrighted by Informa Markets. Our speaker is solely responsible for his content and opinions. On behalf of our guest, John Francis, I'm Michael Krieger. Thanks for your time. Have a great day.